Of course, Gödel in 1931 and Turing in 1936 shows it couldn't be done. But I'd like to discuss using a formal axiomatic system to prove what the bits of a real number are. Now, if the real number is uncomputable, let's say you can prove what every bit in an individual real number is. You name it, and you can prove maybe the 6th bit is 0, the 9th bit is 1. If the formal axiomatic system always enables you for a particular real number that somehow you can refer to or name, if the formal axiomatic system always enables you to prove that individual bits are, 0 and 1, and if the formal axiomatic system doesn't prove falsehoods, then I can compute a real number by looking for a proof of what every one of its bits is. In other words, if I can always prove what a bit or a digit of a real number is, then I in fact have an algorithm for computing it digit by running through all possible proofs until I get to a proof that every digit I want, every next digit, what it is. Okay? So if you have an uncomputable real, it turns out there's incompleteness. You cannot prove what every individual digit or bit of the real number, what the expansion is. Because if you could always prove what each digit or bit is, then you have, in fact, an algorithm to calculate it, digit by digit or bit by bit. In fact, there must be infinitely many digits or bits that you fail to prove what that digit or bit is, because if there are only finitely many bits that your formal axiomatic system fails on, or digits that it fails to enable you to prove what it is, you could just have a table on the side that says these are the missing digits or bits. So, and then you would have an algorithm using that table for the finite number of digits or bits, and adding to it a formal axiomatic system which enables you to prove what every other digit or bit in the binary decimal expansion is. Then you could compute the real number digit by digit or bit by bit, and we've just assumed that it's an uncomputable real. So an uncomputable real has to have the property that for infinite many digits or bits, if you're working in binary instead of decimal, no formal axiomatic system can enable you to prove what the value of that individual digit or bit is. The 7th, the 8th, the 9th is 0, 1, 8, whatever. Okay, now what if we go from an uncomputable real, which is Turing 1936, to an algorithmically irreducible real, which is one of these? What happens if you try to prove what the bits or the digits of the decimal or binary expansion are of this number? Well, it's very easy to prove. It takes a little more effort than the argument I just gave you, but it's very easy to prove that a formal axiomatic system can only get finitely many digits or bits right. And in fact, if your formal axiomatic system itself has n bits, you can't get much more than n bits right. That's basically how it works. Or if you work in digits, you want to have the formal axiomatic system, the information in it, somehow comparable in size to the information in the real. And if you do that, basically it turns out that for an algorithmically irreducible real, thank you. Thanks a million. Plus all the wine has a dehydrating effect. So, excuse me. So the result is, in general, for an algorithmically irreducible or random, shall we say, real number which satisfies this definition, any formal axiomatic system can only get finitely many bits or digits, prove what they are. And in fact, if you're interested in the details, an n-bit formal axiomatic system, that's the program that generates all the theorems, that goes through all possible proofs. An n-bit formal axiomatic system can only just about get n bits of a algorithm of a random real. Which means essentially the only way to get the bits of a random real is to put them into the axioms directly, which means you're not using reasoning. Okay? So these are bad guys if you're trying to prove what the bits are. So the question is, why should I believe in such a real number if I can only, not only I can't compute it, already Turing did that in 36, but I can't even prove what individual bits are for more than a finite number of bits of that real number. Why should I believe in that real number? In what sense does it exist? Why should I take it seriously? So there's an even worse case. Of course, one of the problems is how do you name or refer to a specific random real number? I said that most real numbers with probability 1 are uncomputable and also satisfy this definition. But to have an incompleteness result, you have to refer to a specific one, right, somehow. And you can't say the random real number I picked out from a hat, because every time you do it, it would be different, right? You need to have some way to refer to one real number again and again to get an incompleteness result here. And in fact, I have a way of doing that. I was able to show that if you talk about the halting probability of a computer, that gives you a particular real number that satisfies this definition. So Turing has a famous 1936 result which says the halting problem is algorithmically unsolvable. There is no algorithm to decide if a program will halt or not. Well, halting is easy. You run it and you're patient. The problem is to prove that it will never halt, right? So if instead of looking at individual programs and asking is there an algorithm to decide whether it halts or not, if you look at all possible programs and you have to put a probability in some natural way on the set of all possible programs, and that has some technical difficulties. You need the programs to be self-delimiting, an instantaneous code, a prefix-free set. I don't want to get into the technical details. There is a natural way to talk about the probability that a program generated by coin tossing halts. And the result is that you can define a real number between 0 and 1, which is the halting probability of a program generated by coin tossing. And that probability turns out to be one particular algorithmically incompressible real, and then this incompleteness theorem that I just gave you becomes operative, because it only works if you can name an individual real. You know, and saying that reals with probability 1 have a property that's bad, involving proving what their bits or digits are, has no significance if there's no way to name that real in the assertion. Well, anyway, that's there's an even worse result having to do with real numbers from this point of view, and that's the fact that most real numbers cannot be named even, because or defined or specified even non-constructively. Now, why? Well, if you're using a formal axiomatic system or a formal language, or you can even talk about Portuguese or English if you want, but then everything becomes vague. But the point is that all possible assertions in a language with a finite alphabet are countable or denumerable, right? So let's imagine in our heads, therefore, that you have this enumeration of all possible assertions, and you look through them for all possible ways to name a real number, or every time you specify a real. And it could be completely non-constructive, the way I specify or give a name to an individual real number. But the point is, all the nameable reals or the definable reals, even non-constructively definable reals, all the reals that can be specified uniquely or named uniquely is only a countable set. And therefore, using the same argument, you know, it's a set of measure 0, probability 0. With probability 1, a real number is not going to be nameable individually. Why? Because they're just too, I was going to say goddamn many, real numbers. You know, there are much more real numbers, because it's a continuum, than there are possible texts in any language, a formal language or a natural language. That's only countable, you see? And we know that any countable set of reals has probability 0, right? That's a trivial assertion in measure theory. You know, any countable denumerable set of reals has 0 probability, because I showed you the covering here. It's not a difficult mathematical argument. So the question is, I claim this is a strong incompleteness result, but do you buy it? Gödel, let's compare Gödel with this result, that you can't name, with probability 1 you can't name a real. Well, what is it that is incomplete? Your ability to name reals. Now, in Gödel's incompleteness theorem, what's incomplete is your ability to prove true assertions, not about reals, but about piano arithmetic, about 0, 1, 2, 3, 4, 5, in addition to multiplication. So that's much more concrete. And what you can't do is you can't prove all true assertions, arithmetic, number theoretic assertions. And in this incomplete result is vaguer, because I'm talking about real numbers, and I'm saying that no formal axiomatic system or formal language can somehow individually name all possible reals. So, you know, I happen to think this is a significant theorem, but, you know, it's